In this video, we're going to solve the K of concentration from pressure info. Remember that in equilibrium calculation, there are Kc's and Kp's, whether you're using concentrations or whether you're using pressures. For a gas problem, generally we are thinking using Kp values. However, we can still calculate out a Kc value for it. In order to do this, we'll need an equation. Remember that your Kp is equal to your Kc times RT to the power of the change in the number of moles in the balanced reaction. Given this info, take a minute, see if you can't solve what is our pressures at equilibrium, what is our Kp, can we turn that into Kc? Go ahead and try that and come on back. All right, if you're back, solve Kc directly from pressure data isn't something we can readily do. Pressure data is going to give us Kp. If we know Kp and the change in moles of our balanced reaction, we can solve Kc. So in order to do this, we need to know Kp. But Kp is going to be equal to the partial pressure of the product, N2O4, divided by the partial pressure of the starting material, NO2, squared. This means I need to know those partial pressures. Well, I know the initial pressure of NO2, and that was all that was added initially. And I know that the final pressure at equilibrium is 112.3. So the pressure's gone down. If we think of the equation for a minute, that makes sense. I have 2 moles of gas becoming 1. Every time 2 particles do this, I lose 1 particle in the gas phase in terms of total particles. So as product is formed, I should reduce my total pressure. Well, initially, we had 200 torr and none. There was only 200 torr added of our starting material. There's a change. I'm going to lose some starting material, 2 times X. Whatever amount I'm losing, we'll say I gain that much, just X of our product. And so I have to lose 2 starting materials for every 1 product we form. At equilibrium, that'll be 200 torr minus 2x torr, and that'll be x torr. Well, we know the total pressure. What's the total pressure? It's going to be the sum of the 2 things. So 112.3 torr must equal the 200 minus 2x plus the x. It must equal whatever's left of our starting material plus whatever amount of product we have. Which really means that 112.3 torr is going to equal 200 minus x. Minus 200 from both sides, adjust the negative. Our x is going to equal 87.7 torr. This means that I can find that partial pressure of the N2O4 at equilibrium. It's going to be 87.7 torr. And I find that partial pressure of the NO2, it's going to be 200 minus twice that, or 24.6 torr. This means I have my partial pressures. I can solve for Kp. My Kp is going to equal 87.7 over 24.6 squared, or 0.14492, which means we now have the value for Kp. We can solve Kc. 0.14492 must equal Kc times RT to the change in moles in our balanced reaction. Well, we start with 2, we end with 1 in terms of our gas moles. So change in moles is going to be minus 1. Our R value, our pressures have been in torr, so 62.36. Our temp was 298 Kelvin. which will be 18,583.3 to the negative 1. Divide that across. Means that our Kc is going to be equal to 2,693. So using our pressure data, we can solve Kp, and then we can use the relation of Kp and Kc to solve Kc. Let's do this one additional way. We did find the partial pressures. Well, that pressure is going to be a pressure no matter what size container we have. So we can pick any size container and we can find the moles for that pressure of each gas in that container. So let's just pick 1 liter. Our pressure times our volume is equal to nRT. We can solve the moles of each gas, and then we could divide it by the 1 liter. We could get the molarity. It's not dissolved in water, but it is still a moles per volume measurement. Well, molarity is generally what we calculate out our Kc's in. We can mimic this by taking the partial pressure of each gas and dividing it by RT. So we can find the concentration of NO2 instead of its pressure. I just need the 24.6 torr over 62.36 torr liters mole Kelvin times 298 Kelvin. The concentration of my NO2 is 0.001324 moles per liter. Technically, that's how many moles we have in 1 liter. We move the volume over, but keeping it as 1 means the moles are the same as the concentration in this case. So in our 1 liter container, this many moles, so there's this many moles per liter. I can also do this for the N2O4. It was 87.7 torr over 62.36 and 298, making it have a concentration of 0.00472 mole per liter. Does that make sense? Well, I've got a little over 3 times the pressure in the same container, and my concentration is a little over 3 times the concentration. So it looks like our calculations are holding consistent there. This gives us concentration values. Well, our Kc is just going to be products over reactants, but in concentration forms. So our N2O4 over our NO2 squared, which will be 0.00472 over 0.001324 squared, which if we calculate will give us 2,693. So we get the same Kc whether we use the direct relation of Kp to Kc through the change in moles in RT, or whether we actually take those moles and the volume they're in, find the concentration of each of those reagents in that volume, and plug them back into the Kc equilibrium expression. Kp equaling Kc times RT to the change in moles is a faster way to accomplish this, as it adjusts for those differences in moles between products and reactants for us. But we can still calculate them out to see that they do give us the exact same value. And so we can solve Kc from pressure data if it is something that we wish to find. Often with gaseous reactions, we just use Kp anyways. But there are reasons we may wish to talk about the concentrations within the reactor.